Thank you very much for the introduction. So I'm going to tell you about these crickets that we've been working with that do a acoustic vibrational duet. So you're probably all familiar that in most crickets, the male sings, produces an acoustic signal, and females walk to find the males based on that sound. What we're working with is a small tribe of crickets that is highly diverse, and instead what happens is the male produces a song, the female produces a vibrational signal, and the male is the one that walks around and eventually finds the female. So this is just an example of a video showing you what the female does when she hears the male song. The male song is just a single pulse of high frequency sound. So you can see it just basically looks like a little push-up, and it's at a very rapid latency after the male call. Or we can watch it slowed down as well. Okay, so I was really interested when I first saw this to figure out how did this start? How do you go from males singing, females walking to males, to males singing, females doing a push-up, and males finding females? So to test hypotheses about the origins of signals, we need to have a good idea of the evolutionary relationships, so a good phylogeny, and also a lot of data in order to actually do ancestral trait reconstruction, which we don't have yet for this group, but this is what I would like to do. So what we know is that within the family Gryllinae of crickets, the ancestral state is males singing, females doing phonotaxis. And then we have this subfamily, the Eneopterinae. And what's interesting about them is they start to put a lot of energy in their song into the higher frequency harmonics. So whereas the Gryllinae and tree crickets are having most of their energy at 5 kilohertz, these Eneopterinae are putting equal amounts of energy at 5 and 10 kilohertz. And then we get to this special tribe, derived tribe, the Lebinthini, and the males are putting all of their energy into the high frequency harmonics, so their calls are all 12 or 13 kilohertz or higher, some are ultrasonic, and the female does a vibrational signal, the male does searching, and the female has completely lost phonotaxis as far as we can tell from about 10 species that we've looked at so far. So there's two hypotheses for how this could have evolved. The first is an acoustic startle response. So this is what we started with a while ago now, 2015. The idea that this calling song with the loud high frequency components could actually startle other crickets, creating this vibrational signal that then evolved into their communication system. Another hypothesis that is recently suggested is that actually this could be due to courtship behaviors that then get produced at greater and greater distances until it becomes actually the long distance signal. So this is what we would like to test, these two hypotheses that are not necessarily mutually exclusive, but I'll first show you what we thought of for the acoustic startle response. Basically, crickets have the ability to kind of use categorical perception to identify low frequency sounds, typically as good sounds, so males singing, something they would walk towards, and high frequency sounds, so sounds above 12 kilohertz as being bad. And when they're flying, they will actually fly away from the high frequency sounds. And what we found is that if you play a high frequency sound to one of these typical field crickets when they're standing on a surface, they startle. So this figure is an example of a Lebinthine male song on the lower trace, which is a high frequency sound. And the upper trace is a laser vibrometer recording of the vibrations that were generated by the startle response of that cricket. And then for comparison on the right, what we see is the same male call and the female vibrational reply that occurs within this species. Okay, so what we also noticed is that the tuning of the female vibrational reply is all tuned to higher frequencies, so the females don't respond if the song is at low frequencies, and they do fairly broadly to higher frequency sounds. And this kind of nicely mirrors some of the neurobiology that we know about these crickets. So They have sort of a low frequency tuned auditory neuron that is involved in mate finding, and a high frequency tuned interneuron involved presumably in predator detection. So this is summarizing the acoustic startle response, what we have for it so far. Basal on the phylogeny, we have these startle responses to high frequency sounds. We've looked at this intermediate group, so the Eneopterinae that have some high energy in the higher frequency harmonics, and some species startle and some don't, which is interesting. And then in the Lebinthini, they do not startle at all. So they have basically lost this startle response to single pulses of high frequency sound, and they only produce the vibrational reply in a mating context with the song of the male in the correct temporal pattern. Okay, so the courtship hypothesis is suggesting that vibrational signaling is very common during cricket courtship. In addition to that, in many cricket species, the males will produce calls that have a lot of energy in the high frequency components during courtship. So in the case of crickets, courtship is when they're physically close to each other. And so the Lebinthine system could have originated from these courtship behaviors that then evolved to be produced at greater and greater distances. So we've started to test this. We use an arena where we can visually see what they're doing, record the vibrations and the sound, and we just looked at 2 Gryllid species so far. And these are examples then of courtship song. At the top we have the spectrogram, at the bottom is the oscillogram. And the spectrogram, you can see that the male is producing quiet song at these low frequencies, around 5 kilohertz, but it's throwing in these loud, high frequency sounds as well. And these are actually very loud, so 85 to 105 dB at the female. So this is just to remind you of what the Lebinthine system looks like. We have this male that produces a trill in this case, and the female produces a vibrational reply. This is what we saw with Gryllus bimaculatus. They're throwing in these high frequency sounds, but we were not observing vibrational signals afterwards. The vibrational signals that we did see were the male producing really big vibrations, and this has been documented in this species before. And same for Acheta domesticus, it was the male that was doing all of this vibrational signaling, and I understand there's going to be more information about this species coming up later, which I'm looking forward to hearing. So to summarize what we know about this, we have not documented female vibrational signals during courtship, but that I'm putting yet because we have literally just looked at 2 species, which is absolutely not enough. Mia, who will talk tomorrow about her experiments, has not observed vibrational signaling in females within the Lebinthini during courtship. But this actually could be supportive of this hypothesis if it's something that got co-opted for long-distance signaling. What we don't have any data yet is for this Eneopterinae group in the middle, which is essential for us to actually know what the ancestral state was for these crickets. So this is what we are working on right now. I want to thank my students and technician and my collaborators and all of you for listening, and I'm happy to take questions if there's any time.